I actually submitted a couple of presentations, but this was the only one that enough people voted on, I guess. Am I talking loud enough for you guys to hear me? Okay. I don't really talk that loud by default, and it's been several months at least since I've done anything like this. So I'm a little uncomfortable at it, but I'll do my best. All right, so unfortunately, this presentation is probably going to suck really bad because I didn't have as much time to prepare it as I wanted, and I kind of got halfway through and then I'm not sure what we're going to do from there. I think what will happen is, well, that doesn't matter. So at least now that I've told you, okay, now what I need to know is how many of you have any sort of experience with Python? So pretty much everybody. Okay. How many of you have ever used numpy or scipy before? Okay, you guys will probably be really bored. You can go do something more interesting if you want. Or actually, if you want to stay, I might call on you to think up something interesting to talk about. Okay. Let's just go to a presentation. Maybe you'll be confused for about the next 15 minutes, but that's okay.
Would you increase the text size on the terminal?
Yeah, I'll do that in a minute. Wait, no, that's not what I wanted. All right. So, numpy and scipy, big deal. You know, what are computers really for? So, numpy is designed to answer the problem of you want to do stuff with numbers. It's a little more specific than that. I mean, it always is. And then scipy is just like a bunch of routines and a bunch of libraries that you can use to do things that mathematicians typically do, or people that use math in an applied sort of manner. All right. So I'm going to spend some time talking about something that doesn't have anything to do with numpy and scipy. To just sort of motivate what I want to say. So first of all, data, what is it? I have a few different definitions there, and you can argue about what it means, and whatever, it's sort of irrelevant anyway. So the first definition, data is information, and the meaning of the information is defined by further data. You could call metadata. So a little more information on what metadata means. It gives meaning to your data. It gives it structure. Data is just a bunch of numbers, and those don't mean anything. All by themselves. If you want to find meaning out of it, well, that's a different story. If you want to impose meaning on it, you have to have metadata. So I'm just being really particular about what metadata means. So I'm a physicist by nature. I was in graduate school for a long time, and then I left because I was I decided I didn't want to be told what to do anymore by the hazing known as graduate school. But I double majored as an undergraduate in physics and math. So that's the way I sort of look at the world. Is there's physics and math. There's scipy and numpy. So you have physical reality. I guess I call it physical nature. And data is what I decided to call it an abstraction of physical nature. So what does that mean? So you want data is numbers, but you want to do something with nature. If you want to do anything useful, you observe almost immediately the numbers that you think you're looking at are not the real numbers, whatever those are. I don't think anyone really knows. I mean, and then so these two observations have to do with how do you quantify or qualify what it means, what it is you're doing. So first of all, the numbers that you come up with, suppose you're Newton. I am Isaac Newton and I'm measuring gravity. So I have my pendulum and a stopwatch, and I count the number of times it moves. And then there are some formulas I can use. But the problem is there's going to be an error there. There's going to be some difference between the number that I come up with and what's really going on. Assuming there is something really going on, which I won't really get into. Okay. So error is the problem is error is an unknown. So in order to quantify it, there are some tricks you can apply from probability. So you measure it a bunch of times, you have a statistical sample, and then you can apply things like the law of large numbers. Most likely you'll get a Gaussian distribution. Well, if you know all your errors, you'll just get a Gaussian distribution. So data, the metadata provides meaning for the data. What does that mean? Well, I would like to submit that this meaning comes in the form of a structure. You deliberately prescribe this structure by saying, I'm going to measure this several times. So what do you have? You have a table. Or I guess what I wrote down is if you're doing something really interesting, like you're looking for the Higgs boson, you have a lot of tables and many dimensions. Each dimension has a meaning, association to it. So you want to look at reality, you have data, and you design it to be a table because that's useful. All right. Another way to do it is, so suppose you're running a website and you want to look at data associated with your website. That data is going to be pretty much stochastic, meaning it's gonna happen at so there's two ways to divide time. There's stochastic and there's periodic. So stochastic is anything that's not periodic. That's the way to think about it. But this data is going to be, whether you're looking at a web server or you're looking at the dynamics of distant galaxies, like their rotation speeds and that sort of thing, there's going to be the metadata there. Data is still tabular. So this is basically what I said already. The relations that define the dimensions of a table of data, data structure, is the metadata. Metadata gives your data meaning. So why the crap am I talking about all this? Oh wait, I'm not supposed to ask that yet. So the next thing is, So the reason your data is already motivated, you know that. You're gathering data for whatever analysis you want to do. But why? Why are you gathering this data? You want something out of it. What is that? You want an answer. An answer is a single thing. How do you get something single out of all this information? So the way that you get there is, this is a very familiar idea for anyone who's done any sort of programming. You have information and you have actions that act on that information. So I'm calling those morphisms. I probably shouldn't have used that word, but whatever. So data is used to generate, project. So there's a single conclusion, or maybe a small set of conclusions. So how do you get to that conclusion? Well, you have reason to believe that there's some sort of magic in this data. There's some sort of other information. Once you set up your data in a structured way, then you can see other things in there. And that's what you're usually looking for. And so I'm calling that a trend data, but that's also data. So it's sort of meta like that. And the utilities that you use to find this other information, to do any sort of actions, is called a morphism. You can also think of them as functions or maps, or they may be very complicated, like you're doing an integral or a Laplace transform, but those are constructed of simple atomic operations that are basically just simple sort of maps. Okay. Oh, I keep going on here. So there's one other topic I want to bring up before we get to numpy. That is a special kind of data structure called I'm going to call it a tensor. Although in a certain way you can also construct tensors of morphisms, but whatever. Okay, so tensors are useful because they're associative, commutative, distributive. Like when you're doing arithmetic, you don't even think about the fact that, suppose you're adding two numbers, 3 and 5, 3 plus 5 equals 5 plus 3. You don't think about this. This is so intuitive. But when you're dealing with more complex things, you don't necessarily get this for free. So people spend a long time to try to figure out a way that we can get this sort of easy way of working with things. Because by nature, humans are stupid, and we need simple things to work with. So what is a tensor? Here are some examples. Probably not very good. So these are rank 1 tensors. Oh, I should have put in rank 0. A rank 0 tensor is like an integer, a scalar, right? It's a better way to think of it. So this is position in space-time. You have your space and time coordinate. And then there's velocity. This tau here is the proper time. If you take c to infinity, it just turns into a more conventional notion of velocity and acceleration. Here's some rank 2 tensors. This is the metric tensor for flat space-time. This is the rotation around the z-axis. So if that way is x and this way is y, and then this way is z, and you want to rotate space some angle theta, then this is the operation you apply to all points in space. It's a tensor. And then if you want to do, there's, just for completeness, I put this other one in here. if you want to do a similar sort of rotation into time, it's called a boost. There's this boost angle phi. So relations between space and time. Oh, I'm sorry, I should say. So look at this top one. The rows are called, are they vectors or covectors? I forgot. No, the columns are vectors. So look at the first column. This position is t, time, and then this is x, y, z. And then the covectors, this is time, x, y, and z. So I don't really expect you to understand what a tensor is, but hopefully this one sort of makes sense. In fact, if you ignore time altogether, you might have seen that matrix before. And finally, example of rank 3 tensors. So the Kronecker symbol is like the identity matrix. Well, let's look at the Levi-Civita symbol for a second. So this one is a 3 by 3 by 3, and in the first face there's like there's a -1 here and a 1 there, and in the second one there's a 1 down here and a -1 up here. And you can define this in terms of a couple of rules, but it's so much more illuminating to actually see what it is that you're working with. This symbol is very, very useful. You can define the cross product in terms of it. It makes a lot of multidimensional things simplified in terms of the expressions that you're using. So those are examples of 3 by 3 by 3 matrices. So if you want to think of the Kronecker symbol or the identity matrix, in the blue face in the front you'd have a 1 here, and in the red one in the middle you'd have a 1 in the middle, and in the green one you have 1 down here. So it's like sort of like a more general notion of the diagonal of a matrix. And so maybe you're thinking tensors are matrices, square matrices. That's sort of true. They also have to satisfy some properties, but that's basically the idea. Okay. Now, why did I spend all that time? I spent the last 5, 10, 15 minutes of your time sort of rambling on about data and the philosophy of data. But now you can't get those 15 minutes back. You have this picture in your mind of well, hopefully you have a really firm idea of what it means to be working with data. So, and the conclusion I want you to have is, and you can argue about it, I don't care, whatever. But the conclusion I want you to have is that data is essentially tabular by nature. You cannot have data without it being tabular. So, how does numpy handle this? In numpy, there's a class called ND-array, and that's what you do everything with. Okay, so why is NumPy fast? Python is not fast. Well, Scython, is that how you say it? CPython? Oh, it's CPython? Okay. I preferred Scython, but whatever.
Scython's a thing too.
It is? Oh, okay.
It's much faster.
Okay, CPython then is not fast because when you write your Python program, you have all this crap in it, and for some reason that extra step of compilation on the fly makes it slow. I don't really understand all that stuff. But what I do understand is something very simple. In NumPy, you create an ND array, and NumPy will set it up in a way such that you have this very static thing in memory. And there's this notion of a stride. What that means is So like, if you look at one of these examples, there's a lot of symmetry here. There's 3 columns and 3 rows and then 3 faces. But usually the way a computer works is, in a really simplistic sense, is one-dimensional. You think of the Turing machine. You have this string, you have this strip of information, and you have operations that operate on it. The Turing machine doesn't operate in more than one dimension. So how do you, but data is essentially tabular and multidimensional. How do you handle that? Well, so what NumPy does is, stride is like a boundary, or like a row of your table. So everything's really fixed, static, no dynamic stuff going on. So computation and complexity is reduced. That's, in my opinion, that's about all that NumPy really does. I mean, it does more, but like the essentialness of what you're doing with it is just pretty much that. Okay. So now I'm going to increase the font here. Let's say 17. Is that too big?
No, that's good.
Okay. Sorry, I don't have SSH key set up. Okay. The next, that's really dim, isn't it? Maybe I'll like change the background or something. Or you can turn the lights down, Jordy. Okay. So, how many of you have ever used Ipython before? It's pretty nice, although sometimes it gets annoying. Can everyone see that? Okay. Good. So, first thing, let's just do. Why am I doing this? Because that's traditional, and typically computer algebra systems just have a ton of functions in the global namespace. So there's a lot. Okay. So first, let's go here. So let's create a data structure, or just some data container called A. So there it is. There's your string of data. And we want to impose, let's say, that this is actually a matrix. So, or we can do something else. NumPy doesn't really care. That's the conclusion here. NumPy doesn't care what your metadata is. It just looks at it as a string of numbers, and you tell it what the dimensions are. NumPy calls it a shape. So let's do one more really quick. Let's say I want something three-dimensional. 15 is not divisible by 3 integers simultaneously. So let's say 2. We want to do 30. So that's 3 times 5 times 2. Yeah. Right? 10 times 3. Yeah. 30. Okay. And then so right now it's one-dimensional. Let's make it three-dimensional, and then we'll specify this the frequencies. Let's say 2, 5, 3. There you go. Five columns, 3 rows, 2 faces. So let's see. There's some other basic functions let's talk about. So the number of dimensions, let's do that. Why is it coming up as 1? Oh, sorry. Three. The storage type, or the type of number that's in there, integer. These are internal types to NumPy necessarily, because Python types are not C types, that's for sure. All right. Anything else in the NumPy land? So there are other convenient ways to construct data structures. Now, let's take a more concrete example for a second. Suppose you are doing a typical experiment that you would do in an undergraduate physics class or whatever. Let's say you're measuring gravity and you have a pendulum. So you need to know the length of the pendulum and the mass of the object at the end. However, the angle that you swing it at is irrelevant if you want to measure gravity. So you have this pendulum. You need to measure the time and the the period. So you perform the experiment several times, and what you end up with if you perform an experiment several times is just a simple two-dimensional table. So what are you going to do with that table? Normally what you do is maybe the first thing you do is you want to know what your data looks like. You want to find these trends that you're interested in. And an easy way to do that is to plot it. So you take 2 or 3 elements out of your 2 or 3 columns out of your table, and you plot them. So you have 2 columns. Those are your x and y pairs, and you apply that on a scatter plot, and then you see, even though it's just a bunch of dots, you see that there's some sort of other structure going on in there. Or you can do that with 3 columns or 4 columns, or however many you want to look at. So the next thing that you do is what? You have the structure, you want to find it. So suppose then your scattered dots is sort of like a, too bad I don't have a marker. So even though it looks like a bunch of dots, it sort of looks like a line. So what do you do with that? You think, well, there's got to be a line in here, and some very smart people have thought about this before, like Gauss and Euler, and they came up with these really amazing methods for finding the function in your data. This is called, usually it's called minimization. Okay. Where is it? Optimization? No. I was just looking at it. Maybe it is optimization. Yeah, maybe that's it. I remember looking at that. Oh, yeah, here we go. So, unconstrained minimization, there are various algorithms. Most of these are probably based on linear regression, which is a method of least squares, which is invented by Gauss. There's many, many others. You can look at the chi-squared. You can look at the log likelihood, other sorts of things like that. Okay, so that's an example of working with an array of data, a two-dimensional array of data, and you're finding a trend in it. Scipy has these functions that you can do that with. Yeah? You want it bigger?
Oh, no, maybe it's statistics.
Oh, yeah. Yeah, that's a good idea. So, at this point, here you are. Here's a directory of what Scipy does. And it's sort of a laundry list of everything that typical applied mathematicians work with. Basic functions. You have things like Bessel functions and Legendre polynomials. Lots of the error function. And then there's sort of specialized operations that you do, like integration, interpolation, Fourier transforms, signal processing. So we have 15. We have 15 minutes left. That's about all I prepared. So what should we do next? Who already has an idea of what they want to learn about? Or if you just came here and you figured I'd give you everything, I mean, that's probably the way it should be, but I sort of didn't prepare all the way. Yeah?
So how does it deal with like none values? Like when you're working with the database, you'll have null values, and it'll just drop back to the operation.
I'm not sure. I think, well, Scipy and numpy have their own internal notions of integers and complex numbers and that sort of thing. You probably have to scrub that, sanitize that before you put it in. Yeah?
Does Scipy have like methods to numerically solve differential equations or anything like that?
I believe so. I was just thinking about that, but I didn't see that in this list. What kind of differential equations are you thinking of?
I don't know, just like solving Poisson's equation or something like that in different coordinate systems.
Poisson is
Del squared. Phi equals rho or whatever.
0? Or wait, 0 is the Laplace equation.
Mm-hmm.
Yeah, okay. So just
things like that.
I believe so. I was looking for that.
Yeah, I don't see anything obvious in the list. You might think of it as like a multi-dimensional optimization problem, right?
Right. Well, there's a lot of ways you can think of that, depending on what you want to get out of it. So, does anyone have any specific uses of scipy in mind that you want to talk about? Or if not, if you just came to learn about it, that's okay. Yeah.
Here's a simple problem, just an instance of taking maybe two different two-dimensional shapes, maybe two parabolas, and seeing where they intersect, if at all. Is there some kind of built-in function?
So, well, there's a lot of ways of doing that.
Yeah, I just like to have like a package that I guess that kind of wraps.
So, let me review your question to make sure I understand. You have. Actually, can you just say it again?
Yeah, so you have some, two-dimensional surface, and you have, let's say you have one straight line and you have a parabola, and you just want to see if the line intersects the parabola, and if so, then where.
Okay. Well, I don't know. The way I do that is I just write down the equations for those and solve it. So that I wish I could write on the board.
That had like a wrapper that could, if that was already coded somewhere, and I could just put in the data.
So would that be linear algebra, solving a system of equations?
Yeah, that sounds promising. Oops.
Sounds like it.
This would be numerical, right? Scipy is just numbers, right? No symbolic.
Right, that's my experience and understanding. Yeah, so I guess you just create those functions and then
write it as a system of equations.
Right. Of course, there's a lot of other linear algebra stuff in here. Okay. Let's see. How many of you don't know what a Fourier transform is? Okay. Let's look at that really quick. That's interesting. So, dang it, I really wanted to write on the board. Sure, that would be nice.
I'll be back.
So a Fourier transform is it's an operator. It's an integral operator. So you take a function and you integrate out an entire variable from 0 to infinity or from minus infinity to infinity. Well, these are it's talking about Fourier series here. So the canonical example is, suppose you have a wave and it's going like this because it's several waves on top of each other, and that wave is a mono recording of the Berlin Philharmonic in 1944 under Wilhelm Furtwängler, or it's me talking right now. What a Fourier transform does is you take the entire sample, you say minus infinity to plus infinity, we'll integrate over time, and we integrate it with this function. Well, you integrate it with, I don't remember exactly the layout of the function, but what it does is it finds all of the frequencies and the time.
It's going to be e power I 2 pi j omega t. I know this the frequency.
Yeah, well, the 2 pi, there's a normalization. Is that always there, or you can there is a choice for that? Anyway, so a Fourier transform will take, so this is your source data. This is time. It's some sort of periodic plus stochastic information, and you find out what's in there. If it were purely stochastic, in this case, you have the frequency, and this is arbitrary normalization. Let's just say you take the highest peak and you set it equal to 1. let's see, it's right there. And then these are all the frequencies that are in the sound. If it's purely stochastic, if it's purely random, I mean, what does that really mean? That's an interesting question. Are you just going to get a rectangle? If you look at a violin, you have a certain signature. So this is what a Fourier transform does. It's useful in getting. It's useful in help. It's very useful in a lot of ways to a lot of different things. But one example is, suppose you have a sound wave and you want to know what the component waves are. Well, then here you go. Here's the frequencies. You know the frequency. If you know the frequency, you know the period, and then you can sort of get the amplitude from this. Let's see. Anyone else have something you want to ask or bring up? Yeah.
Keep asking questions.
Sure.
Somebody else does, but
Go ahead.
What is sparse graphs and sparse data structures? How do they work with?
I haven't ever done anything with that.
Okay.
You mean this one?
Well, I understand that
Oh,
the general idea is you have maybe just a few data points,
yeah.
and you don't want to, say maybe you got a matrix that's like 1,000 by 1,000, but you only have 100 data points. So you don't obviously want to take up 1,000,000 bytes just for 100 data points.
Right.
And so it's some way of storing that in only 100 pieces. And I was just wondering what effect that had on calculations.
Well, you'd have to have a little more than 100. You have to know what the data is, and you have to know where it is. So I'm not sure how that works, but that's like a second order. So we talked about strides, and you said it here. That's what they are. So that, to me, that sounds like a sort of a second order optimization on that sort of thing. That's a good question. I'm not sure exactly how it's implemented, though. Yeah.
How prevalent a tool is Scifi and numpy used among mathematicians? Is it pretty common, or are there more like
Mathematicians, and from my experience, tend to be pretty conservative in what they do, and so that means a lot of them just use what's given to them. Well, I shouldn't generalize like that. Most mathematicians will just use MATLAB or Maple because that's what they're used to. I don't have to explain to this audience what the advantages of Scipy would be over Maple or MATLAB. Scipy is obviously much more equivalent to MATLAB than it is to Maple, whereas Maple tries to do everything. MATLAB is a numerical package. Yeah.
Have you heard of Stage?
Yes.
So, I have my doctorate in mathematics, so
Uh-huh.
I've been in the community, and that's the big open source Sage that I've seen being used.
Yeah, and that's also Python, right?
Yeah, it's based on Python. It's really similar. I think if you've used Ipython and Ipython notebook as a notebook,
Yeah.
it's supposed to be kind of like a drop-in for Mathematica.
Oh, okay.
Is the way I understand it.
Is Sage then mainly focused on symbolic math as opposed to number crunching, or does it?
Well, I don't know what it uses in the back end. Like Sci-Fi, I know is using numpy, so they're going to things that are fast.
Sage, as I know, is trying to be all things so.
Yeah, it's pretty broad. A lot of people I know, I studied pure mathematics, so it was very much just abstract stuff.
Well,
Pretty much anything that you sit down and say, okay, I'm going to teach a calculus class, or I'm going to teach a differential equations class.
yeah, Maple tries to do that. Scipy uses NumPy, which uses LAPACK, which means a linear algebra library, and there are a lot of different implementations of that. Most interestingly, if you work on the big iron, there are very, very meticulously optimized libraries in Fortran and C that are very, very fast. Yeah.
What about PyPlot, I think it's called?
PyPlot?
How does it use the Scifi and numpys?
PyPlot?
It's
Okay.
It's
It's part of Matplotlib.
Oh, okay. Yeah, so Matplotlib, well, MATLAB is sort of a complete package, and it includes a plotting function as well. So Matplotlib is sort of like the plotting equivalent of. So if you think of Sage as a open source implementation of Maple, then scipy and numpy, scipy plus numpy plus Matplotlib is like the equivalent of MATLAB. And I think it's a different project, but it is pretty fully featured. If you want a plotting library, I find it kind of annoying to use. To give you a comparison, I went back to GNUplot because I didn't like Matplotlib. And GNUplot is really arcane in its syntax. Whenever I need to do anything that I don't know how to do, I just have to look at an example. But it is a really nice plotting library, and maybe it's a lot better than the last time I used it. Yeah.
So I was just curious. I'm not too familiar with either one. I've used Matplotlib a tiny bit, but
Yeah.
what do you feel that GNUplot has that Matplotlib? Why did you?
It's just a much more mature package, and I think people judge it a lot based on the default terminal that looks really ugly. But I think the real power of GNUplot is, well, like the different backends that you can use it with, like SVG or whatever, and you can style it that way. It also has some functionality like time axes that Matplotlib didn't have at the time. So, okay, last question, and then I won't make you guys feel awkward for leaving. Yeah.
No, I was just letting you know there's.
Okay. Yeah. Thanks for coming, and even though it was boring, I hope you found some interesting things to learn. Thanks, Brady.